So in this lecture, lecture number 7, we discuss on simple module. In previous, we discussed on quotient module and different isomorphism theorem. Isomorphism theorem in quotient module and quotient of quotient and then quotient of sum. And we also discussed the free module and the basis of a module and other aspect also. There are some transformation, there are linear functions in this. So now we discuss on simple module. What is simple module? So first we have to know what is called maximal submodule. So it is like a maximal ideal in ring, same as similar to maximal ideal in ring. It is actually maximal submodule. And this name maximal means it is clear that if M is a module and this N is another submodule, a submodule of N, so N is called maximal. So N is maximal submodule. So in maximal means in some sense a maxima. There is no such thing which is bigger than N. That means first of all N must not equal to N, and there is no such module between N and M. What is the meaning of that? So if there is a module P, submodule P, if P is another submodule, if P is a submodule and P lies between N and P, then either P is N or P is M. So no other submodule between N and M. N and M are different and no other submodule in between M and M. So that in that sense is called maximal. So we should not say maximum. We should say maximal. What is the difference between maximal and maximum? It is like a tree. It's a tree structure. Say 0 is here, the lowest submodule, and M is somewhere here, so highest. Now there is say one module, say N1, which is a superset of 0. 0 is a submodule of N1, and maybe here other N2 maybe, but maybe N1 and N2 are two distinct, or maybe N1 does not continue N2 and N2 does not continue N1. So maybe say here N3, maybe another submodule say N4, another submodule say N5, maybe N5, N1 and N2 is N5 maybe N1 plus N2. In that case, if N1 is N5 is N1 plus N2, then N1 is a submodule of N5, N2 is submodule of N5. Same it may be say N6, it may be say in N7, something like that. This is also called chain condition in module, and maybe that M is the last thing, the highest. M is the every module is submodule of M. So maybe you can directly go to here, or maybe say N7, N8, like that. This is a tree structure. It's a graph structure. And what is this maximal? These are the maximal thing. These 5 are N8, N5, and N7. These 5 are maximal submodule. Why? Because there are no other submodule between M and them. But N6 is not a maximal. Because in M and N6, between M and N6, there is submodule N7. All are distinct. Now, why not is maximum? Because N7, everything is not less than N7. So you can't compare between N5 and N6. That's why in that sense it's a maximal but not maximum. So maximal means there is no other thing which is bigger than that. But maximum means everything is less than that. These two are different. I can say nothing is bigger than that, but I can't say everything is less than that. It is true if it is a linear order. You know it is a linear order, then it is true. But it is a partial order set. If it is a partial order, there is a partial ordering. For the partial ordering, it is not true. Like a divisibility. For divisibility, so we take all the divisor of 30. Now, other than say 30. Now 15 is the maximal, but 15 is not the maximum. Every divisor of 30 is not a factor of 15. But no other than 30, nothing is multiple of 15. So in that sense, 15 is the maximal, but not the maximum. Like same thing, you can do it with say in mark sheet. Say there are some students which give exam in say statistics and mathematics. Now I will say someone is maximum if he or she got the maximum highest marks in math and stat both. But if someone get maximum marks in statistics but not in mathematics, then we will say it is a maximal student is a maximal student, because no other one student is better than other if he beat the other student in both subjects. But it so happens it beat one subject but lose by the other subject. So that is uncomparable. You can't compare them. One student got 19 statistics, 18 mathematics. Other is got 85 in statistics, but say 95 in mathematics. So you can't compare. In that case, we will say maximal, not maximum. You know, it is for the case of partial order set. So that's why it's called maximal. A similar idea for the minimal. What is the minimal thing? Same thing. So n must not equal to 0, and any submodule which between 0 and n, that implies either p is n or p is 0. It is called minimal, so it is a minimal. Now the definition of the simple module. Simple module has only two submodules, 0 and n. It's like a field. Field has only two ideal, the field f itself and the 0. If for a ring there are only two ideal, no commutative ring with identity. If commutative ring with identity there is only two ideal, then it is a field. Usually for any ring which is has one but may not be commutative, if it is the ideals are 0 and itself, then it is a division ring. Now there is a two equivalent condition. Any minimal submodule is simple. Obviously, any minimal submodule is simple because it is a minimal. So see, n is the minimal. So no other submodule is there other than 0. N and 0 is the only submodule. N itself is a submodule. N is submodule of n, and 0 obviously is submodule of anything. But there are no other submodule because it is minimal. So minimal submodule is simple. What about the maximal? Maximal may not be simple because between m and n there is no submodule, but between 0 and n there may be infinite many submodules. So what is the result? The result is again is very trivial, that if m mod n, m quotient by n is simple, then n is the maximal submodule. So if n is the maximum submodule, if and only if m mod n is simple. So this is a quotient module. Why this is so? It is clear that we know that in m mod n, what are the submodule of m mod n? We know that if p is a submodule of m which contain n, then p mod n is the submodule of m mod n. But there is no such module. That means is no such between m and n. So if either p is m or n, m equal to n, p equal to n. If p equal to n, this p mod n is just null mod, that 0 module. And if p is m, then it is just m mod n. Similarly, if this is the simple, then there is no such module between these two. So if p mod n is between these two, then either p mod n is m mod n or p mod n equal to 0. So since p contain n, that p must be either n or n. So in both ways it is if and only if. So it is trivial to show that any submodule is maximal if and only if m mod n is simple. Now there is a very important, interesting result called Sullemma. What is Sullemma? This is very important in module theory. If m or n are two simple R module, both are same ring R module, then any R linear map from m to n is either 0 or an isomorphism. So if m or n two simple submodule, simple module, n has no other module other than 0 and n, m and no other module other than 0 and m, then any R linear map f is R linear map is either 0, 0 is the one linear map, and isomorphism is the another linear. Now, in particular, if if you take the endomorphism, that means if you are taking M to M, then this endomorphism thing, that endomorphism means the set of all function, all linear map from M to M, which is isomorphism, then this collection is called endomorphism ring, and this is a division ring. This will be a division. Why this is true? Now, this is slightly non-trivial. How do you prove that? Suppose f is a linear map from M to M. Now, f may be 0. F is a 0 function. Everything goes to 0. F of x equal to 0. But okay, still, till that, let that f not equal to 0. So we have to prove that f is isomorphism. F is isomorphism. If it is not 0, then it is isomorphism. So if it not is 0, that means there is at least one x. That there is at least one x0 in N, such that f of x0 is not equal to 0. So at least one x is there. Now, what is the kernel? What is the kernel of f? So kernel of f, we know the kernel of f is a submodule of M, right? An image of f is the submodule of M. Now, since kernel of M is a submodule of N, now there is only two submodule of N. It's either 0 or N. Now, what about if kernel is 0? If kernel is 0, that means every element goes to is 0. No, sorry. If kernel of M is N, what is this? If kernel of N is N, what is the meaning of that? That means for every x in N, f of x equal to 0. So that means it is a 0 function. So it can't be true. So kernel of N is a contradiction. Is a contradiction. Because if kernel of f is N, then every element of N, fx is equal to 0. But we assume that f not equal to 0. At least there is at least one x0 in N, so that f of x0 is not equal to 0. So kernel of f cannot be N. So what happens? So then kernel of f must be 0. And since kernel of f is 0, we know this is a injective map. Kernel is 0, it is injective. So we prove that it's injective. Now we have to prove this onto. How do you prove it's onto? Similar way, that range of f. What about the range of f? The range of f is again submodule of M. Now again, it can't be 0. If it is 0, f of n is 0, that means f is 0, the 0 function. That means fn is M. Oh, it is onto. So this is trivial. So it's trivial to show it is onto, but slightly work is needed to show it is injective. So it is injective and bijective both. Since M or N both are simple. If it is N is simple, M is not, then we can say F is injective. If M is simple, N is not, then we can say it is onto. But if both are simple, it is injective and onto. Therefore, it is isomorphic unless the function itself, the 0 function. Now, what about it is a division ring? Now, in particular, if M equal to N for endomorphism, so M and both the module is M, so M is a simple R module. Now, the function is either 0 or isomorphism. So that's collection of this all set of f such that this is R linear. What are the collections? The collection contain only 0 element and all isomorphism. Now we know this endomorphism is a ring. Clearly it is a ring. We saw in the previous videos that endomorphism is a ring. Set of is endomorphism group, that set of all endomorphism is a ring. Set of all endomorphism is a ring, and that is called endo-M. Now this ring has what element? 0. And all other element which is not 0 is isomorphic. But we know if someone is isomorphism, inverse exists. Then an inverse is also R linear, and inverse is also isomorphism. If it is R linear, if it is isomorphism, the inverse function is also R linear, and it is isomorphism. Now there's the inverse exists. So since there is inverse exists, every element other than 0 has inverse exists. That means a division ring. It may not be commutative, but 1 is there because you have the one means the identity map from M to N. So 1 is there. So in the ring, 1 is there. Every element other than 0 has inverse because all elements are isomorphism. That means it's a division ring. Commutativity may not be there. It's a division ring. So this is very interesting and important theorem for simple ring. Now there is an important proposition or result is this: if an R module M is simple, if and only if R is actually isomorphic, this symbol is for isomorphism symbol, M and R mod I is isomorphic for some maximal left ideal I in R. So you have to clearly understand that what is the statement. So an R module M, so M is an R module. That R module will be simple if and only if R M can be written as R mod I. And if I is an left R module, you know that R mod I have a module structure. If I has a left, if I is a left R module of M, then R mod I has a module structure, and that module is isomorphic to M for some I, and I is a maximal left I. On the other hand, if M is a module, R module, and I is a maximal left ideal, then R mod I is a simple R module. So it is both way. That means you have first M is given to you. Say M is given to you, and R is given to you, and M is given to you, and M is R module. Then we can find I. Then we can find I such that, and I is a maximal left ideal of I R, such that that M that is given to you is isomorphic to R mod I, and R mod I have a module structure. If it is I is a left module, it may not be maximal. If it is a left module, then R mod I has a module structure. But that I can be choose as a maximal left ideal. Number one. On the other way, conversely, now M is not given to you, or maybe okay. First of all, say assume that M is not given to you, R is given to you, and one maximal left ideal is I is given to you. Then R mod I has a module structure, and that module is simple. Number one. Number two, maybe so happen that R is given to you, I is given to you, and M also given to you, such that I is a maximal left ideal in R, M is a R module, and M is isomorphic to R mod I. In that case, M is simple. So the converse can be stated in two different ways. The one direction is easy. If M is simple, you can find the I such that I is maximal left ideal, and M is isomorphic to R mod I. That is one thing. The other way, from right to left, we can state in two different ways. We can say that, okay, I have a R ring, and I have a maximal left ideal in R. Then R mod I is a module structure, and that module is a simple, number one. Or you can say like that, okay, I have a R, and I have a maximal left ideal I in R. R mod I is a module structure, and some module M is isomorphic to R mod I. Then M is simple. But this is actually these two are equivalent, because if R mod I is simple and another module which is isomorphic to R mod I, that also simple. So if some module is isomorphic to a simple module, that module is simple. So we can think M is there or may not be there. The same thing. So there is nothing to no harm if we assume that there is no such M. We have to prove that just R mod I is a simple ring, a simple module. That's enough. No need of M. One way. The other way, you need M, because then you have no I. You have to find that. So this is both way. If and only if. So what is the proof? Proof is again not trivial, but is easy. Suppose the one way you choose M is isomorphic to R mod I. For some maximal ideal, we take the right hand side. then what happened? You know that R mod I is not equal to 0 because it is maximal. Since it is a maximal, I is not R, not 0, but it is maximal. What is the meaning of maximal? There are no other left ideal between R and I. That means this R mod I is an R module. It is R module, and that R module has no other submodule other than R mod I and 0. Because if there are any other submodule in R mod I other than R mod I and 0, then there is an ideal between M and I. But I is maximal, so there is no such other submodule. The only submodule of R mod I is either 0 or this. But since R mod I is not 0, we have only exactly two submodules, 0 and R mod I. Therefore, R mod I is simple. By definition, it is simple. And since R mod I is simple and M is isomorphic to R mod I, M is simple. Since it is simple and isomorphic module must be simple. Now, conversely, you have to go from left to right. So you assume that M is simple now. We assume that M is simple. Simple R module. Obviously, since it is simple, M is not equal to 0 and no other submodule between M and 0. Now take a element x0 in M. Any, let this. And x0 not equal to 0, say. So x0 not equal to 0. Now take the module generated by x0. What is the module generated by x0? You know, this is the generating set. x0 is a generating set which generates the submodule. It's called the submodule generated by x0. Now, since x0 is not equal to 0, this is not equal to 0. There are non-zero elements are there. Now, x0 is a submodule. So, since x0 is a submodule, so 0 and this is not equal, then x0 and this is submodule of M. But we know M is simple. Since M is simple, that means x0 is equal to M. So if M is itself generated by a single element x0, that means M is free and cyclic. This is also called cyclic R module. This is called cyclic R module. And this is free. So M is cyclic and free R module. Now what you have to show? We have to show that M is isomorphic to R mod I. Where is the I? Where is the I? We have to find the I. We are in M now. So we have to find the left ideal, maximal left ideal in R. So how do you find? So now we are defining a function, a map. Now we are defining a map f such that f from R to M. And that map is f of A is from R equal to Ax0. Ax0 is M. Now this is onto because M is just generated by x0. So any element of M is like A into x0. So this is onto. Now this is onto map. Now what is the kernel of this function? Kernel of this map. Now kernel means set of all A in R such that, A in R such that Ax0 is 0. So that means it is annihilator. It is the annihilator of x0. And we know this in ring theory that annihilator of x0 is a maximal left ideal. So it is a maximal left ideal. This kernel is the maximal left ideal. Maximal left ideal. So since annihilator is maximal left ideal, we have this kernel is the maximal left ideal. Number one, we have this. So our I is just the kernel of F. We have to choose I as the kernel of F. Now we have to show that R mod I, that when R mod kernel of F is isomorphic to M. Now this is the first isomorphism theorem. You know this, if this is a onto map, since F from R is itself R module. So there is a R module R itself and M is the right hand side, and this F is the onto map, and that means your R mod that kernel of F, which is you choose as I, this must be isomorphic to M. This is the first isomorphism theorem in the previous class. You prove it. You prove that if that R linear map is onto, and then that R mod or whatever that domain set mod that kernel is isomorphic to the range set. So this actually proved that this R is something maximal. Let M is isomorphic to R mod I, where I is that kernel of F. So we have to properly choose the function. Actually, we have to cleverly choose the function such that that function creates find the I, what will be going to be the maximal sub left ideal, as well as that M is isomorphic to R mod I. So next we are going to think that cyclic module. Again, cyclic module we defined in the previous slide that cyclic module M is called cyclic if and only if that it is a definition that M is just Rx. So every element of M can be written as A into X. Every element of X for a single X. So one single X can generate all these things. So like a cyclic group, we say it is cyclic module. So the cyclic module by definition is this. An important result is that if R module M is cyclic, if and only if M is isomorphic to R mod I for some left ideal. Now it may not be maximal. So if it is a simple, then it is maximal. If it is not simple, it's just for any left ideal. For some left, not the any, for some. May not be for all left ideal, but for some ideal. At least one ideal is there. So again, it's a both way. Again, if M is cyclic, we can find I, and if I is some left ideal, then R mod I is cyclic. Or there is any, if R mod I is cyclic and M is isomorphic to R mod I, then M must be cyclic. So this is a very important and interesting result in model theory. So how do you prove this? How to show that this is true? So before prove that, we just say something about that annihilator. What is annihilator? So annihilator of R module is just set of all A in R so that M equal to 0. So it's annihilate this. And if M is a cyclic module, then it's a singular same thing. So if M is Rx cyclic module, then we just write other than annihilator Y, we write just annihilator X. So which annihilate X, which also annihilate M, because M is nothing but AX, or BX, maybe just any element of M is just BX. And that element annihilate that BX is actually, if A annihilate BX, then A annihilate X. So because this is 0, A into BX, A is annihilator of BX, so A into BX is 0. So you just write as ABX. So AB annihilate X. So we just write this. If it's a cyclic module generated by a single element, we write this, and we can easily prove that annihilator is a left ideal. That is also easy. Now, a cyclic module is called free if it is free. Okay, first is faithful. So just R module may not be cyclic, is called faithful if the annihilator is 0. 0 always annihilate this. So 0 into anything is 0. So 0 always there in the annihilator. 0 is there. 0 belongs to this set. 0 belongs to that. But 0 is the only element of this set, there are no other non-zero element which annihilate this M. So if you take any non-zero element, then A, so then M not equal to 0. So if this is not so, if annihilator is only element is 0, there are no other element which annihilate M, then this that M is called faithful R module. That M is called faithful R module. So it's faithful if the annihilator is 0, no other element, just kill all the element of M. And again, if it's a finitely generated R module, M is called finitely generated R module. If M can be written as some n many finitely many R module, but each are cyclic. So that means if Mi is generated by Ri, that means Mi equal to Rxi, then M1 is generated by X1. So that M can be written as some A1x1 plus A2x2 dot An xn. That means every element of M is generated by X1 x2 xn, linear combination of X1 x2 xn. In that case, we say this X1 x2 is a generating set of M. So M is a finitely generated if there is a finite set which generates M. What is the meaning of that? That means every element of M can be written as a linear combination of this finite set of X1 x2 xn. And that is actually nothing but just the sum of M1 into Mn, where M1 is just generating by the X1, M2 is generated by the X2, just AX1, set of all AX1 is M1, set of all AX2 is M2, like that. So it is finitely generated. Next is, oh, yes, this is there. A cyclic module is free if and only if annihilator is 0. If annihilator is 0, then it is free. Some book is taken as the definition of free module. We can take two definitions. We can put that a cyclic module is called free if M equal annihilator of X equal to 0. One thing is this, or you can define like that. That free module we defined in the previous video, that free module which has a basis. So actually these two concepts are equivalent. That means if a cyclic module has a basis, then annihilator must be 0. And if annihilator is 0, then that must have a basis. Now, cyclic module means is X generates M. So generator is there. So you have to only show that this is actually unique representation. So every element of M can be written as uniquely in X. Now this is clear. So every element of M, if it can be written as two different ways, AX and BX, if there are two different choices, then A minus BX, A, B are in R and X is in M. X is the element of M, which generates at M. Now this is 0. Now since annihilator is 0, if we assume that annihilator is 0, then A minus B is 0. So because A minus B annihilate X, so A minus B equal to 0. So A B equal to B. So unique. On the other way, if annihilator is 0, then the now it is proved that if annihilator is 0, then it is unique. Next, we have to show that if it is unique, then annihilator is 0. Now, if annihilator is not 0, we will show the contrapositive thing. If I say annihilator is not 0, we already proved that if it is annihilator is 0, then it is a unique representation. Unique representation means it is a basis. X is the basis for M. That means it is free. We took that definition in previous video. We took that definition as a free which have a basis. Now this basis has only one element because it is cyclic, generated by a single element. Now the other way, if annihilator is not equal to 0, then we have to show it is not a free. So annihilator is not equal to 0 means, so there is an element, say y in annihilator such that y not equal to 0. What is the annihilator? So okay, let's take B, because the element of R, so element of R may choose as B. Since B not equal to 0 and B is the annihilator of X in annihilator of X, so Bx equal to 0 by the definition of annihilator. Now bx equal to 0, and 0 can be written as 0 into x. That means 0 has two different representations, as a bx where b not equal to 0, as well as 0 into x, two different representations. So it is not a unique. So this is not has no basis. So this x is not a basis. Obviously this x is not a basis, but you can say there is any other basis, but no, there is no such other basis also, because if there is a basis, and if say there is a basis, say x1 x2 xn is a basis of this Rx. Now every element of x1 x2 xn actually is generated by x, so x1 is nothing but some a1 x, a2x just a2x, like that. And this cannot be independent, because if a1 not equal to a2, if a1 equal to a2, then x1 equal to x2. If x1 equal to not equal to x2, that means a1 not equal to a2. And since a1 not equal to a2, this can be independent. So like that, because a2 x1 equal to a1 x2. But in that case, we need that this is a commutative ring. No, we need commutative ring for that. Otherwise, how do you show that this is independent? How do you show this is true? Because this is x2 x1x, this is x a1 a2x. So how do you say this is equal if our ring is not commutative? Okay, you have to choose that ring is commutative, right? Here you have to choose R is commutative. Otherwise, you can't say this result. You have to assume that R is commutative. So since R is commutative, then I have to think a little bit on that. If R is not commutative, is there any counterexample or not? Okay, let's start. For time being, we assume that R is commutative. So in that case, this cannot be independent. So that can't form a basis. So basis with just only one element. If there is basis, that must be a single element. And if that single element, and if annihilator is not 0, then that single element can generate R, it can generate M, but that representation is not unique. So this is the important result on simple module. And what is the theorem left with? That thing, that R module is cyclic if there is some left module for M is isomorphic to R mod I. How do you prove this? How do you prove this? Just let's think. How to prove this? So, okay, first we assume that M is cyclic. Oh, we are going the same direction. Say M is cyclic, so M equal to Rx. Now again we can define a function like from R to M, like say A goes to Ax, right? Now what is the kernel of this? Kernel of this is just onto mapping, and kernel is a left ideal. Okay, it is a left ideal. Since kernel is a left ideal, and this is onto because M is cyclic. Since M is cyclic, every element can be written as A into X, so it is onto. Now kernel of F is left ideal, so just for the first isomorphism theorem, M is isomorphic to R mod I. Okay, the one part is done. By the first isomorphism theorem, R mod I is M, is isomorphic to M. By the first isomorphism theorem, the kernel is choose as a I. What is the other way? Other way to show that this is cyclic. So we have to show that if R mod I is cyclic, we have to show if I is some left ideal, we have to show that R mod I is cyclic. Why R mod I is cyclic? Not be its maximal. Why R mod is cyclic? Some left ideal. Why this is slow? Is it if and only if? Oh. Okay, I have to think on that. Next video, I'll maybe something say on that. Okay, I stop this video here. Just one thing is left out, that if M is a R module and for some left ideal I is there, then we have to show that R mod I is cyclic. Whether if it is not true, then we have to just take the only one-sided if. But if it is if and only if, you have to show the other way. We already showed one thing. If M is cyclic, then we have this. That we got. We have to show the other direction. And you have to think whether it is true or not. Okay, we'll discuss on the next video. I'll stop now.